So here's a quick review of everything gas chemistry, which probably won't actually be that quick, but I'm going to try really hard to go fast. So we base our prediction of the behavior of gases on this idea of the kinetic theory of gases, which is just kinetic is all about moving. How do gases even move? In reality, gases are real, but we pretend like they are ideal, and that allows us to ignore some of the factors that influence how the gases behave. It allows us to simplify our predictions. The things that we like to pretend, the assumptions that we make about gases, they are very small. The gas particles are very, very small, perhaps even non-existently small. And we also like to assume or pretend like those gas particles are separated by lots and lots of empty space. So gases don't really run into each other very often, and that allows us to make lots of predictions about their behavior. We also assume that they're moving in straight lines and that when they run into each other or into containers, that the collisions are elastic, which simply means that all the energy that the particles have going into a collision are transferred to the particles as they exit the collision. And this is the big one. We also assume that there aren't any forces of attraction. And if we're talking about gas particles not actually having mass or volume, then of course there wouldn't be any forces of attraction. This is the thing that starts to change how gases behave in reality. Because we know that in reality, gases are small and they're separated by lots of space, but maybe not an infinite amount of smallness and an infinite amount of space. And certainly there will be forces of attraction and repulsion that influence how gases react and behave. So here is a quick animation of gas particles. So here you can see the gases are separated by a fair amount of space, but if I reduce the volume, they get quite a bit closer to each other. There are more collisions. They're closer to each other. They're going to have a bigger, more influential forces of attraction and repulsion. If I heat them up, they move faster. And so gases with lots of heat, lots of space, big volume, big temperature, these are going to behave more like ideal gases. But if I make them cold, they slow down, and you may notice that they end up a little bit closer to each other as they cool off. And so the more time they spend close to each other, and if I reduce the volume and make it cold, you see there's lots of time where they're sitting very close to each other. That's going to increase the influence of forces of attraction and repulsion. So gases that are cold, gases that are under high pressure, small volume, if something is making those gas particles close together, we're going to have less ideal behavior. The gases will deviate from the ideal gas law. And it's all because of those forces of attraction. All right, so let's look at some of those laws that we use to predict behavior. So Avogadro's law states that equal volumes of gases at equal temperatures and pressures will have equal numbers of molecules. So he's saying that if I've got some space, equal volume, and pretend like those cubes are equal to each other, and I keep them at the same temperature and same pressure, regardless of what gases I have in these boxes, I'll have equal numbers of molecules of gas. So maybe here I've got hydrogen gas, and over here I've got like argon gas. As long as I have equal volumes, equal temperatures, equal pressures, I'm going to also have equal numbers of molecules. We furthered Avogadro's law. We now have some quantitative pieces to support that. You know that the molar volume of an ideal gas, so the volume of 1 mole of an ideal gas, it's going to be 22.7 cubic decimeters. Remember, that's the same thing as a liter per mole. So 22.7 cubic decimeters per 1 mole. You could also say cubic decimeters is the same thing as a liter. But that's only at STP, which stands for standard temperature and pressure. our standard pressure and temperature is 0 degrees Celsius and 100 kilopascals. 100 kilopascals, 0 degrees Celsius, that is our STP. So if I have these boxes at 0 degrees Celsius and 100 kilopascals, which is just slightly less than normal atmospheric pressure, and these happen to be cubic decimeter, I'm missing wrong dimension there, cubic decimeter cubes, then each of these guys are going to have a mole, 6.02 times 10 to the 23rd particles of gas in them. So here's a conceptual way for IB to ask about Avogadro's law. So if I have 4 identical containers, same conditions, which means equal pressures, equal temperatures, filled with gases, identical, they've got equal volumes, which container will have the highest mass? So we're assuming that each of these guys have equal numbers of molecules, so really it's just going to be a matter of who has the greatest molar mass. So nitrogen is N2, nitrogen's about 14, so N2 would be about 28 grams per mole. Oxygen is O2, oxygen is 16 on the periodic table, so O2 would be about 32 grams per mole. Ethane, draw it out real quick, is going to be C2H6, which is going to be 24 for our 2 carbons, and then 6 times 1, 6 for the hydrogens. It's about 30 grams per mole. And then neon, I don't remember, I'm going to have to look it up on my periodic table. Neon is about 20, just about 20 grams per mole. Greatest mass, oxygen, right there. Here is a little bit more quantitative version of Avogadro's law. Now we're actually going to have to do some stoichiometry with molar volume. So how many grams of sodium azide are needed to produce this volume, 68.1 cubic decimeters of nitrogen gas at STP? Remember that at STP, molar volume is 22.7 cubic decimeters. And what's kind of nice, we've been given the molar mass. This is molar mass, so this is grams per mole of that sodium azide. So I'm going to go ahead and start my railroad tracks with what I'm given in the question prompt. 6.1 cubic decimeters of nitrogen gas. Always we need to convert to moles first, so I'm going to use this to convert to moles. I know that there are 22.7 cubic decimeters in every 1 mole. Since I have cubic decimeters up here, I'm going to put cubic decimeters on the bottom. Cubic decimeters is equal to 1 mole. There's 22.7 cubic decimeters of the gas in 1 mole of the gas at STP. So now I have canceled out my cubic decimeters. I have moles of nitrogen, but I don't want moles of nitrogen. I actually want sodium azide. So the next step of my railroad tracks, oops, that's a different blue. Sorry, I hope that's not too annoying. I need to flip my nitrogen into sodium azide. I'm going to do that with my mole ratios from my balanced equation. I have nitrogen on top, I'm going to put nitrogen on the bottom. I have a 3 in front of my nitrogen. I want to turn my nitrogen into sodium azide. There's a 2 in front of sodium azide. So now I can cancel out my nitrogen. I am left with moles of sodium azide, which is so close to what I'm looking for in my question. But I need to actually turn my moles into grams of sodium azide. So I'm going to take that mole that I have here, I'm going to put it on the bottom, flip our moles into grams with the molar mass that's given to us right here. There are about 65.0 grams per 1 mole in sodium azide. So now I can go ahead and cancel out my moles. Our only labels left, we have grams of sodium azide, which is exactly what I want to find. So now I do some lovely calculations. 68.1 divided by 22.7. I can actually do that in my head. It's 3 over 1. So now I have 3 over 1. My 3 here and my 3 here can cancel out. So I'm left with 1 times 1 times 2 times 65 divided by 1 times 1 times 1. 2 times 65 is 130. So there are about 130 grams of sodium azide produced in this reaction. So here's another way this molar volume might be proposed to us, assessed of us in an IB exam. So I'm looking for volume of hydrogen gas in cubic decimeters produced at STP. I've got 30 grams of magnesium reacting with excess hydrochloric acid. So I'm going to use my balanced equation here to find my mole ratios. I also need to know my molar mass of magnesium. So I have my periodic table. It is 24.31 grams per mole. So step one, I do need to turn my grams of magnesium into moles of magnesium. I do that by dividing by the molar mass. So now I already have moles of magnesium. I need to flip my moles of magnesium into hydrogen gas. So I have 1 magnesium, oopsie, and 1 hydrogen gas. So my magnesiums cancel out. I have moles of hydrogen gas, but I don't want moles of hydrogen gas. I want volume of hydrogen gas. So I'm going to convert my moles into volume using molar volume at STP. So I have moles on top. I want to put moles on bottom to get it to cancel out. We know that there are 22.7 cubic decimeters in 1 mole. So now I can cancel out my moles. I have cubic decimeters, which is exactly what we want to find. So now I just have to converge all this into a single fraction so that I can match it to my answer choices. So I have 0.3 times 1, I can totally ignore that, times 1, I can ignore that, times 22.7, I'm going to divide that by 24.31 times 1 times 1, I can ignore those two. So it looks like my answer choice is going to be letter B. All right, so now we're going to move away from just Avogadro and talk about all these other guys, which we combine into a single combined gas law. So Boyle is all about pressure and volume, and Charles' law was about temperature and volume, and Gay-Lussac's law was about pressure and temperature, We can actually mash all those together into what we call the combined gas law. Sometimes we throw moles in here too, because obviously if I increase the number of moles in a container, I'm going to change pressure and volume and temperature. But this is basically our combined gas law. This is not in our data booklet, and so this is definitely one of the formulae that you want to have memorized. So when we ask conceptually about this combined gas law, we might see a question kind of like this. Factors that affect the molar volume of an ideal gas. Basically, it's just asking which of these are actually in this equation. Pressure is here. It will affect volume. Pressure, volume. Temperature is here. Temperature will affect volume. Empirical formula is nowhere to be found in our equation. So our answer is going to be A. Pressure and temperature will affect the volume, but empirical formula will not. Here's another question asking us about combined gas law. So again, we have PV over T, PV over T. 1s are equal to 2s. So here is my volume 1, here is my pressure 1, here's my temperature 1. Temperature 2, I've got constant pressure, which means that I can pretty much just ignore. It's going to be 100 here, it's going to be 100 here, divide both sides by 100, I totally get rid of pressure. So I'm really just worried about volume over temperature. Quirky thing about temperature in gas law, we have to always convert to Kelvin. We do that by adding 273. So here I'm going to have 298. And here I'm going to have 323. So my volume 1 is 1 cubic decimeter over my temperature 1 was 298. Kelvin. I'm going to set that equal to, I don't know, volume number 2. My new temperature is 323 Kelvin. So then I can cross multiply and divide 298. The 2's is going to be 1 times 323 is 323. Divide both sides by 298. 323 divided by 298 is not going to be greater than, whoa, it's totally going to be greater than 1. Sorry, I got excited about my division there. 323 over 298 is going to be greater than 1. So neither of those answer choices is correct. It's not quite 2 though, so I can rule that one out, and that is going to be my answer. So I don't need a calculator, but if I want to check my math, just in case, 323 divided by 298 on my calculator is 1.08, lots of decimals, 1.1 when I round to sig figs. Quick aside, the reason that we have to do this the reason that we do temperature in Kelvin instead of Celsius is because Celsius can be negative and Kelvin cannot. There are no negative Kelvins. 0 is 0, absolute 0. There's nothing less than 0 in Kelvin. Whereas in Celsius, we know that we can have negative Celsius. In my car this morning, it was negative 1 degree Celsius. So imagine that I used negative 1 degree Celsius in my car this morning, and maybe it's going to be 10 degrees Celsius this afternoon. If I had a 1 cubic decimeter container in my car, and I want to figure out what's the new volume, well, x times negative 1 is negative x, that's equal to 1 times 10 is 10. Divide both sides by negative 1, and my volume is negative 10 liters? That makes no sense, which is why we have to use Kelvin, because we don't want any negatives. All right, so quick look at this combined gas laws. We know PV over C equals PV over T. That means that they're equal to a constant. If they're equal to each other, we have a constant involved. And ideal gas law pretty much takes the combined gas law, throw in a mole, multiply, I ignore this part of it, and I just take this chunk. If I multiply both sides by N and T, that's going to cancel out. I'm going to be left with PV equals some constant times moles times temperature. This constant we're going to call R. And so now I have PV equals nRT. I know it's in a different order, but basically we have PV equals nRT. PV equals nRT just by rearranging our combined gas law, setting it equal to a constant. But when we use PV equals nRT, we need to use meters cubed because pascals for pressure is equal to joules per cubic meter. So if I have meters cubed here and meters cubed here, they cancel out. If I have joules here and joules here, they cancel out. Moles here and moles here cancel out. Kelvin, and we're left with just a number, which is why this is such an ugly label. All right, so how do we use PV equals nRT? Let's suppose that I've got an ideal gas. I have 390 cubic centimeters, 120 Celsius, 202 kPa's. I want to figure out the moles of the gas in that container. So I'm going to do PV equals nRT. I need pressure, volume, moles, temperature. We know that R is a constant. Pressure, I have 202 kPa's. That's not going to work. I need to have my pressure in pascals. So I know that there are 1,000 pascals in every 1 kPa. So I actually have 202,000 pascals. That's my pressure. Volume, I have 590 cubic centimeters. I don't want cubic centimeters. I need to go to meters cubed. There are 1,000 cubic centimeters in 1 cubic decimeter, and then there are 1,000 cubic decimeters in 1 cubic meter. 590 divided by 1,000 divided by 1,000. Again, I'm dividing by 1, 2, 3, 4, 5, 6 zeros. 1, 2, 3, 4, 5, 6 zeros. And so my volume is actually going to be 0.00059 cubic meters. Moles. That's what I don't know yet. That's my unknown. That's what I'm going to solve for. Temperature is 120 degrees Celsius, but I need to convert that into Kelvin. And so 120 plus 273 is going to give me 393. Good. 393 Kelvin. Just checking my math in my head. So now I'm going to plug in all of these pieces and parts so that I can solve for N. Pressure is 202,000 pascals. Volume is 0.00059 meters cubed. Set that equal to N. I don't know. That's what I'm solving for. R is 8.31 joules per mole per Kelvin times my temperature is 393 Kelvin. To solve for N, I need to divide both sides by all this stuff that is next to the N. We divide by 8.31 joules per mole per Kelvin. I'm also going to divide by 393 Kelvin. If I divide on this side, I have to also divide on this side, 8.31, all that stuff. 393 Kelvin. Kelvin cancels out pascals and joules, and meters cubed cancels out, which means that I'm left with moles in the denominator of the denominator, which is totally the numerator, which is a whole other conversation for a math day. With my calculator, 202,000 times 0.00059. I'm going to divide that by 8.31, divide that by 393, and I get the number of moles equal to 0.036493, lots of digits. Looks like I've got two sig figs to keep, so I'm going to call it 0.036 moles of gas. So now let's say that I've got a mass for my gas. I can use the periodic table to find the identity of the gas with molar mass. Remember that molar mass is grams per mole. Molar mass is always grams per mole. I'm going to take these grams, divide by the moles that I just found. And when I do that division, 0.146 divided by 0.036, I get 4.06 grams per mole. And I look at my handy dandy periodic table and I try to figure out what gas has a mass of 4-ish grams per mole. That would be helium. The identity of the gas is helium. All right, one more quick question on this same topic. So what is the pressure in PA inside? Oh my gosh, lots of pieces of information, and what a hot mess of answer choices. In paper one, you're not allowed to use a calculator. And so instead of asking you to actually calculate pressure, they're asking you to simply set up the problem. So we're still going to use PV equals nRT. I still need to know pressure, volume, moles, my R, my temperature. I'm going to solve for P. That's what I don't know. Volume is 1.0 meters cubed. Awesome, because I need it to be in meters cubed. I don't have to convert anything. Moles, oh gosh, I have grams, not moles. I need to convert my grams to my kilograms, actually, to moles. So 10 kilograms of H2. I know that there are 1,000 grams in 1 kilogram. And then I know that there are, for hydrogen gas, it's going to be 1.01 times 2. So 2.02 grams per mole of hydrogen gas. So 10 times 1,000 is 10,000. 10,000 divided by, let's just round that to 2. I'm going to call that 10,000 over 2. Let's go with about 5,000 moles. I've got 5,000 moles. R is still going to be 8.31 joules per mole per Kelvin. And temperature, I have 25 degrees Celsius. I'm going to add 273 to that. and that is going to give me 298 Kelvin. Plugging all these pieces into PV equals nRT. PV equals nRT. P, I don't know. Volume, 1. Moles, 5,000. R is 8.31. Temperature is 298. Solve for P divided by everything by 1. So now pressure is going to be 5,000 times 8.31 times 298 divided by 1. So this is not it. We definitely don't want degrees Celsius. I can go ahead and rule both of those guys out. 5 times 10 to the 2, that's 500 times 8.31. This is oh so close. I like this one better. 5 times 10 to the 3, that is 5 times 1,000 times 8.31 times 298. This is our answer. Hopefully this helps make us feel a little bit better about gases. Let me know what questions you have.